So in the last section we worked with something called the standard normal curve. A variable, call it x, is distributed with the standard normal curve if it has this distribution. It's distributed normally with a mean of 0 and a standard deviation of 1. So this is your mean, that's your standard deviation. Okay, but you don't have to stick with just a normal, just a 0 and 1 for these parameters here. So this is normally. We can open it up to anything. So I'm going to use this notation for x is distributed normally, so that's an n, with a mean of mu and a standard deviation of sigma. So that's going to be the way I'm going to kind of briefly write things. That's your mean. This is your standard deviation. So we're no longer confining ourselves to just, the one curve, the mean of 0 and a standard deviation of 1. It could be an infinite number of curves, a double infinity if you will, because you have an infinite number of choices for u or mu and for sigma. All right, so what's that mean? It means you can model a lot of different phenomena. There's a lot of different things that have a normal shape, but they're not necessarily going to have a normal shape with a mean of 0 and a standard deviation of 1. Height is something that has a normal distribution. So men and women have different average heights and different standard deviations. But let's try and understand what these things do and represent. And we're kind of lucky that we can do some of this on Desmos. It gives you a nice visual. Now let's start out with the mean. The mean tells you where the center is, where things are centered. Now this one happens to be centered at 0, but I can change that center to anything I want. So when I change the mean of this distribution, watch what happens. You're going to move its center. You're going to move that peak to the left and to the right, and you can make that peak anywhere you want. So it just depends on what the mean is. So the mean is telling you the location of this curve. Now the standard deviation has the same interpretation that it did earlier. What does the standard deviation tell you about some data or a curve distribution? How much variability there is. So the variability reflects how spread out the curve is. Now this is again your standard normal curve, but what if I increase this value here, a, which in this case reflects our standard deviation? Watch what happens to the curve as you increase a. Not only is it getting shorter, but what else is happening? It's getting fatter, more spread out. And that's what the standard deviation does. It reflects how wide a curve is, how spread out your data is. The more spread out, the higher the standard deviation. And as you can see, as I increase this value of a here, larger and larger standard deviation, this curve is more and more spread out. So if I don't want it so spread out, then I can put a very small standard deviation. So, okay, let's do a few problems with non-standard normal curves then. So this is where your handouts are handy because you're not going to have to draw as much. We're going to start with problem number 6. So this is section 6.3. We want to find the area to the right of 91 on a standard normal curve with a mean of 100 and a standard deviation of 15. So this right here. Now the standard normal curve shares some properties with these non-standard normal curves. These non-standard normal curves have a area underneath the curve of 1, and they're symmetric. They're not symmetric about 0. What point do you think they would be symmetric around? Yeah, around their mean, in this case 100. So when I calculate this probability, since 91 is to the left of this, I expect something that's greater than 1/2. because half the area is going to lie to the right of the mean, half the area is going to lie to the left of the mean. So let's draw that on our handout. If you want to borrow a ruler, I've got plenty. They'll be handy here for us. Oops. Zoom out. So in this case, we're working with x, which is normally distributed with a mean of 100 and a standard deviation of 15. So that puts the 100 straight down the middle. Normal curves are always going to be symmetric around their mean. And then I wanted to find the area to the right of 91. So this area here. Now what this would typically mean is that you have to have another table for this mean and this standard deviation. That'd be a lot of work to compile an endless series of tables with different means and different standard deviations. Fortunately, we don't have to. We're going to change this problem over by calculating a z-score and then use the standard normal curve. So how do you get your z-score? Your z-score is going to be x minus mu divided by sigma. So let's see what happens when we calculate that z-score. So for us, it's going to be 100, it's going to be 91. 91 minus 100 divided by 15. So negative 9 over 15. 0.6, negative 0.6. Yeah, negative 3/5, 0.6, negative 0.6. So negative 0.6 is about here. So finding this area to the right of 0.91 or to the right of 91 is the same thing as finding the area underneath the standard normal curve to the right of negative 0.6. So let's work about finding this area. Now hopefully too much time hasn't passed since we've worked with this kind of stuff recently. How do your z-tables work? Do they give me the area in the right tail or do they give me something else? They give you the area in the left tail. So we'll have to keep that in mind as we do our problem. But either way, we're going to look up negative 0.6. So let's find that from our z-curve. So we can go to the negative z-table. So negative 0.6, it's negative 0.60. I'm getting 0.2743 as the area to the left of that point on your standard normal curve. So 0.2743. Oops. 0.2743. Now that's this area to the left. How am I going to find the area to the right then? Yeah, subtract this from 1. So it's going to be 1 minus 0.2743, so 0.7257. Now I was asked by somebody who is about as good as art as I am, are we going to have to draw these things on the test? Well, I'll provide you with what I'm providing you here, and that is these curves already sketched out. I would strongly suggest that you do fill them in because it gives you a rough guide. You know, if you gave me as an answer 0.2743, that should be on your face. You should be able to tell me that's wrong because you know that this probability has to be greater than 0.5. This number is to the left of the mean, and you want the area to the right of it. So it has to be greater than 0.5. And I'm hoping that you can engage in a little critical thinking to reflect on your answer and go, wait a minute, that doesn't look right. This area has to be bigger than a half. Oh yeah, I have to subtract from 1. All right, so that's problem number 6 here. How are we looking on number 6? Okay with that one? What's nice about this is that you don't have to keep around an infinite number of z-tables. You only have to keep around 1. Let's move on to problem number 8. Kind of similar. We're going to work with the same distribution. So that is, our variable is going to be distributed normally with a mean of 100 and a standard deviation of 15. Like I said, this notation is not in the book, but I've always found it very, very convenient to quickly summarize how a variable is distributed. So I'm hoping that you can get comfortable with it yourself. In problem number 8, we want to find the probability that somebody has an intelligence that's between 112 and 124. Yeah, between 112 and 124. So again, let's draw something that's at least reasonably accurate. Sketch in your mean correctly. And the only thing that's really important is that you draw these values on the proper side of the mean. So I have one here at 112 and another one up here at 124. I want to find the area between these 2 points for this curve. I'm not going to do that for this non-standard normal curve. Instead, I'm going to do a little transformation and use the standard normal curve, which is over here. Standard normal curve has a mean of 0 and a standard deviation of 1. I'm going to need to calculate 2 different z-values. One for the 112, one for the 124. So z equals x, which in this case is 112, minus mu, 100, divided by 15. So 12 over 15 is 0.8. And then the next one, 124 minus 100 divided by 15 is going to be 24 over 15. Let's see what. 1.6. Thank you. So let's put those 2 numbers here on our curve. And again, you don't have to really be that accurate drawing these things. I try, but that's just some compulsive disorder in me. What I'd like to see is, a reasonable amount of your work. Let me know that you understand what you're doing here. So we've got 0.8 here and 1.6 here. What am I going to have to do to find the area between these 2 things now that I have similar points on the standard normal curve? I'm going to have to look up both the z-scores, find the areas to the left, and then subtract. So at the 1.6, area to the left of 1.6, find that number, find the area to the left of 0.8. So I'm getting about 0.1661. No. How about 1551? Did I interchange these? 0.9452. Thank you. All right. 452. Ah, rats. Okay, so let me try it down here. 0.9452. And was the other one right? 0.7881. Okay, so 0.1571. So this range on the intelligence curve is close to something called bright normal. Bright normal is about between 110 and 120. So if your IQ is in there, then that's how you'd be labeled, bright normal. All right, I want you to work on one like this. How are we looking for those first two examples, these non-standard normal curves? Let's move to something a little bit different in terms of a distribution. Problem number 22. Now, as background in problem number 22, at the top of this, they give you what's perceived to be the normal distributions for the heights of men and the heights of women. So heights of men are normally distributed with a mean of 69.5 and a standard deviation of 2.4. Women have heights distributed normally with a mean of 63.8. So that's just under 5.4 with a standard deviation of 2.6. So that's interesting. There's more variability amongst the heights of women than there are of men. Moving down to problem number 22. The U.S. Air Force requires pilots to have heights between 64 and 77 inches. Find the percentage of women meeting the height requirements. So, okay. Let's go to the back side of our handout. So the heights of women are normally distributed with a mean of 63.8 and a standard deviation of 2.6. So let's sketch that in a little bit. So the Air Force wants to find the percentage of women that have heights between 64 inches and 77 inches. So this is 63.8, that's 64, and that's 77. So we want to find the percentage of women in here. Now before we calculate this percentage, Can you tell me anything about it? Is it going to be close to 1, close to 0, less than a half, more than a half? Yeah, has to be less than a half. This area lies completely to the right of the mean, so it has to be less than 1/2. So see if you can't finish this one up. Find the z-score for each of those, and then find the area between. Now when you get your z-score, round your z-score to the nearest hundredth. It's important that you round to the nearest hundredth because that's all your table is going to work with, is values to the nearest hundredth. While you're working on it, let me run down the attendance here. Nikolai's here. Hannah. Brian. Dan's here. Chris is here. Meredith. Jordan. Okay. So let's dig up some numbers here. This is going to be 0.2 divided by 2.6, which turns out to be about 0.0769. And that's going to round to about 0.08. Down here, we get 5.07. And we don't even have to worry about rounding that. That's kind of like way off the charts. 5.08. Like I said, it doesn't really matter. That's way out here. 5.08. And then about 0.08. So if you're trying to be somewhat accurate with your graphs, that 0.08 would be probably around here. We need to look up a couple values from our z-tables. So anything 3.5 and up, we're going to use kind of the generic 0.9999. So it's not quite 1, but we'll just use 0.9999 out of a convenience. So 0.9999. And then we want to find the area to the left of 0.08. So 0.0 is right here. 0.08, we'll scroll across and get 0.539 or 5319. And when I subtract, I get 0.4680. How many people got that one? Yay. All right. Looking good. Now there's a couple other parts to this, and one of them is going to lead to some destandardization. Do you want to do another one just like this for the men, or do you want to move on to the destandardization? Move on to the next one is a winner. All right, so what's going to happen next is we're going to go the other direction. We know all the percentiles for the standard normal curve. But if somebody's in the 97th percentile of height here, what does that mean over here when we move back to a non-standard normal curve? So we can find things here, but what does it imply for this over here? So part C says, for Air Force, if the Air Force height requirements are changed to exclude only the tallest 3% of men and the shortest 3% of women, what are the new heights? So I'll do one and let you do the other. So the tallest 3%, well, that's going to be the 97th percentile. So Z sub 0.03, that's our 97th percentile. That means 3% are going to be in the right tail, and then 97% are going to be in the left tail. So 0.97. Now I need to figure out what point this is to help figure out what point corresponds to that in the non-standard normal curve for, I guess we'll start with men. Non-standard normal curve here for men. Their heights are normally distributed in a mean of 69.5 and a standard deviation of 2.4. So what does that 3% translate to over here? Well, first let's find the 97th percentile. That means 3% of the area is going to be in the left tail. What do I need to look up in my Z table? What value should I be looking for from the Z table? Should I be looking up 0.03 down here, 0.03 in here, or something else? Nice, well done. If you take a look at the top here, the top is reminding you what you have in terms of the information on this page. It's going to calculate the area to the left of the z value. Now, if 3% of the area is to the right, that means 97% of the area is to the left. So what I should be looking up is the 0.97. 0.97 right here. Try and find something within the table as close as possible to 0.9700. Should be able to find something really close. All right, I'm thinking we got a winner right here, 0.9699. That's pretty close. I think Dan gave it to us, so it's 1.88. So you look to the left, you find the 1.8 on the left column, the leftmost column, and you look straight up, you find 0.08. Adding those two together, you get 1.88. Uh-oh. Whew. For a second, I thought I was locked, zoomed out. That would have been a pretty big disaster. So 1.88. Now, when we destandardized, or excuse me, when we standardized, when we went from here to here, we used the idea that z equals x minus mu over sigma. That's to go from the non-standard to the standard. If you want to go the other way, if you want to figure out what this value of x is, then I'm going to solve this equation for x. You don't have to solve it. I'm not going to show you the math behind it. It's pretty simple. If you multiply both sides by sigma and add mu, but what you're going to get is a way to go from here to here. And it's x equals mu plus z times sigma. So what's that going to look like for this particular distribution? Well, what should I throw in for the mean? Yeah, thank you. 69.5 plus z, and we just looked that up. Z was 1.88 times sigma, which was 2.4. $74? Okay, sounds good. All right, so 69.5 plus 1.88 times 2.4, 74.012. So basically about 6'2" would separate the upper 3% from the bottom 97%. Interestingly enough, I have a female colleague who is 74 inches tall. She's really tall. And we'll do a little problem on figuring out just how rare that is for a lady to be that tall. Okay. Let's try one more destandardizing one. Any thoughts on this one before I give you one last one? Okay, that one last one is going to be the second part of C here. It says we want to exclude the tallest 3% of men and the shortest 3% of women. So if you're clever, we can save ourselves some work. So if we're trying to exclude the shortest 3% of women, where is that going to be? Yeah, it's going to be on the left here someplace, right? The shortest 3% of women is going to be over here someplace. In fact, if you're thinking about this a little bit, you could probably save yourself some work. What's that value going to be over here? All right, so this is going to be 3% of the area here, 97% here. If you had to, you look up in the z table, and you look on the negative z table for something close to 0.03. But I don't think we have to. Yeah, it's just going to be the symmetric value, right? It's going to be negative 1.88. We just looked up this one. That put 3% of the area in the right tail. On the opposite side of the curve, z equals negative 1.88 is going to put 3% of the area in the left tail. As a reminder, heights of women are normally distributed with a mean of 63.8 and a standard deviation of 2.6. Now it's helpful to have these drawings. I'm hoping that it'll engage a little critical thinking in your mind. Suppose I did this calculation, 63 plus negative 1.88 times 2.6, and I got this for my answer, 68.688. And look at that. Well, that's over here someplace. Would that necessarily be wrong? Well, yeah, we expect something over here, right? We expect something in the left tail. You don't expect something to the right of this. This point is to the left of its mean. So you should end up with something, again, to the left of the mean over here. You're still looking for a place where there's 3% of the area in the left tail, but certainly has to be lower than the mean. What's wrong in this one is I forgot the negative. So let's just go back there and put that in. Now I get something that makes a little bit more sense. 58.912. So 58.912. There. So are you okay with destandardizing these variables? For homework, section 6.3, try problems 3 through 25.